Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's program is In the News. And here to tell us all about it is Stephen Weedy. Steve, so you've got all the hot news from this past year, right?
Well, this is all news from about December 2021. It's not the whole year, it's just some of the exciting stuff that's recent. Relatively recent.
Okay, well, tell us all about it.
So we're going to start with the Hubble Space Telescope. And what's going on there is that in October, all of the instruments went offline because there was a computer glitch. Loss of synchronization. It went into a safe mode and nothing was working. By November 8th, they had brought back the ACS, the Advanced Camera for Surveys, and then the Cosmic Origins Spectrograph and the Wide Field Camera 3, which is the workhorse of the telescope. They were brought back online by December 6th. The Space Telescope Imaging Spectrograph is back, and that was the last one that made the Hubble back to fully operational. That was by December 6th. Now, the Hubble Space Telescope has been in space for 31 years at this point. So 32 years if it makes it to, what was it launched in May, something like that, of 1990. 1990 is a long time ago.
Yes.
So, long missions. The longest mission so far is claimed to be Voyager 1, but I believe Voyager 2 is still going, and it launched first by about a week. On Mars, Opportunity famously spent 15 years doing its 90-day mission, and so on. There's a Mars Reconnaissance Orbiter that's been up there forever. I mean, it's just been up there for a really long time. So we do have some very long-lived space missions. What we really hope is that the Hubble Space Telescope will live long enough to have some overlap, maybe years of overlap, with the James Webb telescope, which is the subject of the next topic.
All right, be interesting to hear all about that. Do tell.
All right, so the James Webb is famous for one thing over everything, which is that launch keeps getting delayed. It's been delayed multiple times for years and years. They started working on this before the Hubble launched. It's amazing, but that is true. That's how it worked. So December 22nd is the earliest that it can launch, but the telescope has been fueled with hydrazine and so on for sort of for station keeping, a little bit of thruster, light thruster fluid for that. And you don't do this until you're ready to launch because hydrazine is incredibly toxic and caustic. If you get some stuff on you from it, you get burned. That's all there is to it. It's really nasty stuff. But it's a monopropellant, and you just open up the valve and you've got a thruster. That's
pretty simple.
It's pretty simple. It is packed and ready to be launched on the Ariane 5, and it is down at the launch site. Down at the launch site is an island off of in the Atlantic.
French Guiana.
Yeah, French Guiana. I think I just don't know how to pronounce it, but Kourou or something like that. In any case, it's there and it's ready to. Last I heard, it was ready to be. It had been put in the. There's an adapter for it to be assembled onto the Ariane 5, and so it's ready to go. So you can still have delays with weather or something, but all of the main things have been taken care of.
Good, good.
There was this issue October 12th where a clamp that was holding the whole telescope broke open and dropped the telescope a little bit. So there was a jarring, et cetera, and there was a delay while they figured out whether it was safe to launch or not, because you don't want to launch a multi-billion-dollar spacecraft if it's not really going to be, to work when it gets there, right? So they wanted to make sure, so there was an extra delay for that. But it was just one of a zillion delays. It was almost like, of course there's another delay.
Exactly.
So, so what are we going to do with the James Webb? Some of the missions are getting a census of cooler objects. This is interesting. That is a man standing in an opening made by, or actually at the edge of the mirror, where each of these hexagons is a mirror segment. So you kind of get an idea of how big one mirror segment, I think it's like 2 meters across, how big one of these things is. Anyway, and then this shot is, you get an idea of, this is obviously on Earth, but you get an idea of, there's this tennis court-sized sort of a reflector. It's an insulator from the sun, basically, and it sits between the spacecraft or the telescope and the sun all the time. So it's always oriented toward the sun, and by doing this, you can keep the whole thing cooler. The spacecraft is going to the Lagrange point 2. This is the Earth-Sun Lagrange point 2. It's about 1 million miles farther from the Earth, away from the sun, right? So the moon at 250,000 miles orbits sort of inside of that distance. At some points, they're all lined up. And you don't actually just sit there at L2. You kind of do an orbit around L2. So you can have lots of spacecraft doing these little orbits around the Lagrange points. And the Lagrange points are sort of gravity-neutral spots, and they're pretty stable. You can put a spacecraft at one of these usually, and it will just stay there without really much effort. You don't have to keep maneuvering to stay there. It'll just do it. And we like L2 for looking away from the sun, especially for an infrared scope, because the Earth is hot, and you want to be away from the Earth for an infrared telescope. Exactly. All right, so we're going to do a census of faint objects, cooler objects especially, like red dwarfs and a brown dwarf, which is kind of a planet or a star, depending on the way that you look at it. Lots of nebulae, so gas clouds out in space. Circumstellar disks. It's a 6.5 meter telescope, so you've got the resolution to actually see stuff around some of the stars. And it should observe some smaller rocky planets that orbit fairly close to their stars. And so we'll get more information on specific exoplanets that we know about already. And it will also, and this is something that was talked about, I think, first, it will also capture light from the very first stars and galaxies that, so at this point, because of the expansion of the universe, the very first, earliest objects, we can see them as they were when they formed if you look far enough away, right? So for that, you need something that has good resolution, and it helps to do infrared because everything is redshifted into the way past infrared. But also, so you want to do all of that, and you want to, in order to get a decent image, get some decent data, and then you need cameras like spectrographs and things like that to characterize what you're talking about.
Okay.
And that's the James Webb. So then the next topic, the next news thing, we have New Horizons back in the news.
Really?
So New Horizons famously went and saw Pluto, and we got some great data on a flyby of Pluto. And then it went on and did a flyby of an asteroid, which I remember as Ultima Thule, but it's been renamed again.
Yes, it has.
And I forget what the new name is, of course. But anyway, in this picture, we're looking at New Horizons, and for this topic, this news topic, what's interesting is the Alice camera. So Alice and Ralph are from the Honeymooners. Exactly. And Alice is the ultraviolet camera, and Ralph is the infrared camera. But here we're interested in the ultraviolet camera because what has happened is that the spacecraft has gone really quite a ways from the sun. Right? So we're here at 1 AU, you know, roughly 100 million miles, 93 million miles, whatever.
Sure.
And what Alice did was it got this map, which is a map of the Milky Way at Lyman alpha, so at the Lyman alpha frequency. And this is radiation that is reflected off of hydrogen gas just that's everywhere, right? So the Lyman alpha spectra, or whatever. And one of the things that we'd like to know about Lyman alpha as a feature is how bright it is. We are so close to the sun at 1 AU that the sun is very bright and reflects off of all kinds of hydrogen and other things right here. And so Lyman alpha is really bright right here. But at 47 AU, 43 to 47 AU, out, New Horizons used this camera to get to make this map, and the scattering from the sun is a couple thousand times, a couple thousand times dimmer, and so you can find out what the Lyman alpha looks like from the Milky Way, and this is something that we've guessed at, and we were wrong by a factor of 20. It's much fainter than we thought. So we'll be able to find out what the component that we've been looking at from the sun is. So that's New Horizons, the Lyman alpha brightness map.
Interesting, interesting. We're going to take a quick break. If you have any questions, please send us an email. We do like to see those, of course. And coming up next is Term of the Month. The term of the month for January is inverse square law. We know that the closer we are to a star or other point source of light, such as a street light, the brighter it is, and the farther away, the dimmer it is. So let's say we have two stars of the same magnitude, but one is twice as far away as the other. You might reasonably think that the more distant star would be half as bright, right? Fun fact, no. The more distant star would only be 1/4 as bright as the closer star. Scientists refer to such a relationship as an inverse square law because as one variable goes up, the distance to the star, the other variable goes down, not by the proportion to the distance, but in proportion to the distance squared. We can see this in the diagram as how this works. S is our light source, and R represents various distances. Let's use light years. At R, we are 1 light year away from our source. Since the change in brightness is a square root function, the square of 1 is 1. But at 2R, we are 2 light years away, and the square of 2 is 4. So the brightness has decreased such that each square only contains 25% of the original light. And by the time we get to 3R, the light in each square is only 1/9, or 11% as bright as the original. Term of the month is square root law. Back to you, Stephen. We're back with Stephen Weddy, who is giving us a look at In the News. So Stephen, I think next up is Tess.
Yeah, that's right. So Tess has found an unusual exoplanet. Tess is looking for exoplanets, and is looking for them in closer stars than we had with the previous big mission. Anyway, it has found this exoplanet which has the density of Mercury. It is the size of Mars, and it has a really fast orbit. It's 8 hours to go around the star once. So back at this image here. The big thing there is the star, and we expect that this red dwarf has lots of prominences and magnetic fields, and it probably does look crazy just like that. And then the planet would be that thing to the lower right. Now, the planet itself isn't likely to have an atmosphere. When you zip around the star in 8 hours, right? This is an orbit. That's its year, is 8 hours. So it doesn't have an atmosphere, so you wouldn't see things blowing off of it. But this is kind of an image of. But this isn't the planet that we're talking about. But this is Mercury, and Mercury is structured with a nickel iron core that is most of the planet, a mantle which isn't very thick, and then a really thin little crust on the outside for the soil and the other sorts of stuff, where the craters are. So this is the size of Mars, and like this. So very dense, a very dense planet. So since it's so close to its parent star, its surface temperature is estimated to be around 1,500 degrees C. You think at least twice that for Fahrenheit. Everything that you know about melts.
Yes.
It's really bad. The atmosphere would be stripped away because it's so close to the star. The stellar wind would be fierce, and it would just push it all. And the magnetic fields from the star itself would wipe out any magnetic field that you'd have, any influence that was holding your atmosphere together on the planet. So there's very little chance that there's an atmosphere. So Tess did some initial, it found it, right? It discovered the planet, but and it did some initial characterization. But there's an instrument called HARPS, which has been used to find planets from a ground-based observatory in La Silla. It's the ESO, the European Southern Observatory, has this telescope with this instrument, HARPS. And HARPS is the High Accuracy Radial Velocity Planet Searcher, HARPS. And so what it's doing is it's doing radial velocity. It wants to see the redshift, or the spectrum shift to the red and to the blue as the parent planet moves toward or away from the Earth, right? And in this case, you would see that for this very nearby red dwarf star being jerked around by a nearby Mars-sized, but probably Earth mass, practically, planet. So you would see that sort of stuff. And you can learn some new things. Since the planet transits, that's how Tess found it, the radial velocity information gives you, you know exactly where the planet is. It's right in line with the star. So you don't have to worry about whether, it might be 15 degrees above or below the plane, the line of sight. You know actually quite a bit about it. And so it was able to give us the density and therefore what the structure must be. It looks like a blob of iron mostly. And we also know that this planet had to have formed farther out than it is, because the metals, even the metals that it's made from, wouldn't be able to form a planet if it were that close to the star. So it had to form farther out, and we do know that planets do migrate. We know that Jupiter, for example, in our solar system, migrated to where it is from farther out, and Saturn and Uranus got moved around by Jupiter as it moved. It actually had moved in quite a ways and then moved out. Jupiter had moved in quite a ways and then moved out to its present position. So it actually moved back out after a while. And there are various physical things that can happen that make these things happen. But we know that this planet around GJ 367, right? So this is 367b. GJ 367b is the current planet's name. But it's a red dwarf star. It's 31 light years from here, which is nearby. It's kind of nearby, relatively
in
nearby,
terms of the
right?
Galaxy, sure.
Right?
Sure.
Astronomical distances, they're huge. So that's this planet. So, and HARPS was able to give us a bunch of the properties that we think that these sorts of red dwarfs typically host an average of 2 to 3, maybe 2.5, kind of Earth-sized planets. And they typically have orbital periods less than 100 days. So these planets, like this one, are easier to find around a smaller star because the star moves more in radial velocity, but also the planet covers more percentage of a small star than a big star. So
this is true.
Yeah.
Just like a bigger goalie covers more of the net than a smaller goalie.
So now that we have found this star, this exoplanet, this planet around this star, this is a good star to look for other planets. So like HARPS might be used to, for a longer study that might uncover other stars, other planets that also orbit there. So next up is IXPE.
Okay.
Different story altogether. So we have a new Xray Observatory, and what blew me away about this story is that I had not heard about this mission until when I was studying, looking for stories. This mission has already launched. So this is an X-ray telescope that has been launched that I didn't know about in advance, and that blew me away. So anyway, IXPE stands for the X-ray Polarimetry Explorer. So what it is polarized light in X-rays. So X-rays are hard to detect. Polarized X-rays are harder to detect. So you have to have a specialized mission for it, a specialized telescope for it. X-rays in general have to be done in space. X-rays don't make it to the ground, which is a good thing for us. So this is what the mission looks like. Hard to tell kind of what's going on, but it will work in concert with other telescopes. One of the things that polarimetry has been used for on Earth was to understand the magnetic fields of the sun, and that was done over 100 years ago. So polarized light has some interesting information. So we want to know what physical processes lead to particle acceleration. Magnetism can be part of that. What are the geometries of flows? So we're getting photograph-like data from this. And of course, what are the magnetic fields? And what are the physical effects of gravitational, electric, magnetic fields at their extreme limits? So when you're looking at a black hole or a neutron star, you're looking at an extreme object. So what's going on really there? So this is an exciting mission, and it went up on a Falcon 9 rocket, and somehow totally missed my radar.
Well, we'll have to stay tuned with this mission to get some more information as we get into 2022.
So it shouldn't be taking sort of routine science data until January. Okay. So we won't find out real soon. Anyway, it launched December 9th. I was just amazed.
All right. Well,
and then finally we have an ion thruster. It's a new ion thruster, and instead of using xenon, or one of the other noble, krypton has also been used, is a noble gas, and ionizing it and then accelerating it electrically out the back. They're using iodine. You know, this is the stuff that you used to put on a wound that, you know, to sterilize it. So it's a liquid. You don't have to compress it like you do, like the gases have to be compressed. You don't have to compress it at all. It's 3 times as dense, so you can have a fair amount of it in a small space. And they've gotten it to work. And so IXPE is a small spacecraft. It's a cube 5 centimeters, this is actually too big, 5 centimeters on a side. It's a 1U CubeSat. And it has this little thruster, it has a little bit of iodine, it has whatever else it needs to communicate and to do whatever, and it's going into space and they're going to test it. And that's going to be, that was also launched December 9th, so that's pretty cool.
It is.
Yeah.
Stephen, these have been some really interesting topics to bring to our viewers and even for ourselves. So we hope that you'll visit our club website. We'll put the address down there at the bottom of your screen. Stephen, thanks for bringing all of this to us. And coming up next is What's Up in the Night Sky. What's up in the night sky for January 2022? Winter is here and the days are slowly getting longer. We'll begin with the moon. We have a new moon on the 2nd. First quarter arrives on the 9th. The moon is full on the 17th and reaches third quarter on the 25th. Now let's take a look at the planets. At the end of the month, the 31st, at 7 a.m., just before sunrise, figure half hour, 45 minutes, Mercury, Venus, and Mars will be lined up and all will be in the constellation of Sagittarius. Now on the 23rd, Mercury is in inferior conjunction with the Sun, but by the end of the month, it'll look pretty good. Venus will actually be best towards the end of the month, as it has inferior conjunction also on January 8th. Next, we have Uranus, Neptune, Jupiter, Saturn, and Mercury. In the middle of the month, right around the 15th at 5 p.m., we will see the other 3 visible planets. We've got Jupiter, Saturn, and, well, Mercury again. Uranus will be in Aries, which you'll need a telescope for. Neptune, also a telescopic sight, along with Jupiter, will be in the constellation of Aquarius. Saturn and Mercury will be in Capricornus, the sea goat. Pluto, who some consider to be not a planet anymore, is still out there, and it's in Sagittarius, but we can't see it because it will be in superior conjunction with the Sun on the 16th. And that's what's up in the night sky for January 2022.